Hey guys, today we're going to learn about tides and how tides work because this is a unit on gravity and astronomical principles. And as you probably know, tides are driven by gravity. So here we are. So today we're going to look at how the moon produces tides on Earth, how the actual mechanism is that makes the moon produce tides. And we're going to look at the idea of whether or not the sun actually produces tides on Earth as well. And if not, why not? And if so, how much? And then finally, what are all the different reasons that tides vary? Because as you probably know, the water rises and falls a couple times every day. And the time of the high tide and the times of the low tide kind of vary from day to day. It's predictable, very predictable, but it's continuously changing. So we're going to start off here with kind of catching up with what you've probably been taught about tides before. And what most students that come to my class have been taught is that the moon has gravity and it pulls on the water in the ocean and it makes the water pile up on the side toward the moon. And then the Earth is rotating kind of underneath that lump, underneath that bump. So we see low tides when the place we're on is not under that lump, and we see high tides when it is underneath that lump. And that's the way that most students are taught in elementary school and in middle school. But is this the whole story? Because when you think about it, if this is all that's happening, we have one big pile of water on this side of the earth. You have a high tide over here and a low tide over here. And that means that once a day we should get a high tide and once a day we should get a low tide. But as most of you know, there are two high tides a day and there's two low tides a day. Every 6 hours, we go from a high tide to a low tide, and then another high tide, and then another low tide. It's approximately 6 hours. So obviously there has to be more to the story than just this. Okay, so here's how it works. Little thought experiment here. Suppose we got the moon. It's out there in space, and we're going to drop two blobs of water out in space, and they're under the influence of the moon's gravity. Now, think for a moment. As these two water blobs fall toward the moon, and they will fall toward the moon because there's gravity there and it attracts them. The question is, will those two water blobs tend to come closer together as they fall in toward the moon, or will they stay at the same, actually I need to go this way, stay at the same distance as they fall in toward the moon, or will they tend to spread out? In other words, yeah, they're both falling, but as they fall in, will they get farther and farther apart? In other words, will the close blob kind of race ahead of the more distant blob as they fall in? So think about that for just for a moment, okay? All right, now the answer to this question is that they get farther apart. As they fall in, the close one accelerates more than the distant one. And the reason for this, as you know, is that the force of gravity depends largely on distance. And if this one is farther away, it feels a smaller pull toward the moon than the close one does. And since this one feels a greater force, it's going to have a greater acceleration, and it's going to accelerate away from the other one. So if we were to attach these with a like a spring, this spring would tend to get stretched as these blobs fell in. Okay. Now, what if we put in a rock? So we bring in a third body. So we bring in a little rock and we put it in right between the two blobs of water. Okay. And we let them go and we all fall, and they all fall in toward the moon. Now, the same thing's going to happen. Now we have three things moving in toward the moon, and as they fall, they're going to get farther and farther apart. And if we tie them together with springs, those springs would stretch. The whole system here, the whole package would be getting elongated, stretched out, like a slinky being pulled apart a little tiny bit. And if we made the rock bigger, same thing's going to happen. It doesn't matter how big this rock is. There's still going to be, as they fall in toward the moon, there's still going to be this stretching force, stretching effect, I should say, because the force on the near blob is stronger than the force on the far blob. And even if gravity starts to become significant between the blobs and the rock, the moon's gravity is still going to pull harder on the blob on this side than one on that side, and it's going to pull on the rock less than the one pull on the rock less than the near water and more than the far water. So it's always going to be stretched, even if there's gravity happening between the three objects here. And if we take it to the extreme and we make this rock as big as the entire Earth, okay, so we have the Earth with water on this side and water on that side, the same effect still happens, okay? The water that is close to the moon is pulled with a greater acceleration than the Earth itself. And the Earth itself is pulled toward the moon with a greater acceleration than the water on the far side. And the result is that the whole system is stretched. And you wind up with water piling up on this side and water piling up on that side. And the reason for this is because the moon's gravity pulls the water away from the Earth on the close side and pulls the Earth away from the water on the far side. And that's the weird thing that's difficult to understand if you don't understand gravity. The high tide on the far side of the Earth is caused by the Earth being pulled away from the water. The water's kind of left behind. And we perceive that as the water piling up. So as the Earth rotates 24 hours in a day, when we're here, this is a low tide because the water's low. When we rotate around to here, now we experience a high tide because we're where the water's all piled up because it's being pulled away from us. Here we get another low tide, and when we're over on this side, then we experience another high tide because the water has been pulled away. The Earth has been pulled away from the water, and the water piles up again. Okay, so this is why we have high tides on both sides of the Earth, and you do need to understand that. So if you need to watch that part again, go ahead and watch that part again. Okay, now what about the sun? Does the sun produce tides? Because the sun is closer to the ocean on this side than it is to the ocean on that side. So it makes sense that we should get this same pulling situation. And the answer is that yes, the sun does produce tides, but the sun's tides are much less extreme than the tides produced by the moon because the sun is so much farther away than the moon. So to go back to here with the moon produces tides because this ocean is much, much closer to the moon than that ocean. The relative distance is very great between the ocean on this side and the ocean on that side compared to the moon. But the sun is way, way farther away. So the percent difference between the near side of the Earth and the far side of the Earth, the percent difference is much less. So even though the sun's gravity is much, much stronger than the moon's gravity, you figured that out yesterday, the difference in the gravity is much less. So the tides that the sun produces are much less extreme, but they do exist. Okay, so when the moon is lined up with the sun and the Earth as in its orbit, when it finds itself here, then we have the sun tides, which are always aligned with the sun. That's the little red ones that I have here. That's the sun's tides. Then the moon's tides are also lined up with those. And the result is that that the moon tides pile up on top of the sun tides. And the result is rather extreme tides. It's the highest high tides that we get because we have the moon tides added to the sun's tides. And we call these the spring tides. Spring tides. That's the most extreme. And you get those when the sun, the Earth, and the moon are lined up. And it can be a full moon. That's what we see when the moon is on the far side from the sun, because we see the bright side of the moon. This is a full moon. But we also experience the spring tides when we have a new moon, when the moon is between the Earth and the sun, and we see hardly anything. We just, if anything, we see a very thin crest of the moon. So the phases of the moon affect the tides. Now, a word about this word, spring tides. This has nothing to do with the season, okay? Spring tides does not mean the season spring. It comes from a different word root. It comes from the same idea of a spring that you find in the woods where water is rising up out of the ground all by itself. We call that a spring, even though springs run year round, not just in the season spring. So a spring tide is when the ocean water rises up a lot all by itself. That's what we call it, a spring tide. It has nothing to do with the seasons. Remember that. Okay, now what about when the moon is at half phase? So we have a half moon. That's when the moon is up here or down here, and we can see half of the illuminated side of the moon. So a half moon. Now, the sun tides are still aligned with the sun because they always are, but the moon's tides are aligned this way. All right, so in this case, the sun's tides are canceled out, or the sun's tides partially cancel out some of the moon tides. So this means that the moon tides are not as extreme because they're working against the sun's tides. Now, the net result of all this is we have the high tides, they're still aligned with the moon, but they're just not as extreme. Okay, so I want to make it clear here. We still have only two high tides and two low tides. It's not like we have a high tide. See, if we drew it like this, it would look like we have a high tide and then a low tide and then another high tide, but not as high as before, and then a low tide and then a really high tide and then a low tide. But like we'd have four high tides, that's not how it works. Okay, the sun's tides are overwhelmed by the moon's tides, and the moon's tides just become less extreme. So it's still a high tide, but it's just not as high a high tide. And we call that a neap tide. It's the opposite of a spring tide. It's the lowest high tides rather than the highest high tides. This also means that the low tides are less extreme. So the variations between high tides and low tides are less when we have neap tides. Whereas in contrast, when the spring tides, we have high tides and low tides. So we have much more extreme variation. And this goes between those about once a week. Because it's about 1 month for the moon to go all the way around. So we have spring tides, and then a week later we have neap tides, and then a week later we have spring tides, and then a week later we have neap tides, and so on, roughly speaking. Okay, what about some other effects that factor into tides? Well, we have elliptical orbits. The moon has not a perfectly circular orbit, and neither does the Earth around the sun. They are elliptical orbits, which means that sometimes the moon is closer to the Earth, and sometimes it's farther from the Earth. And sometimes the sun is closer to the Earth, and sometimes the Earth is farther from the sun. Okay, so when the moon is closer in its elliptical orbit, the tides become more extreme. And that's the moon's contribution to the tides becomes more extreme. And likewise, when the Earth is closer to the sun, then the sun's tides become slightly more extreme, right? And when we combine those two, when the moon happens to be closest to the Earth at the same time that the Earth is closest to the sun, then we get the most extreme tides. We call these the king tides. They happen once a year. It's when the moon is closest to the Earth and when the Earth is closest to the sun. So the tidal effects are the most extreme for both. And when you add them together, you get the absolute highest high tides of the year and the absolute lowest low tides of the year. Those are called king tides. And it turns out that they happen in January. That's when they all light up. You may or may not know or remember from Earth science that Earth is closest to the sun in our winter, in the northern hemisphere's winter. That's in January. So that's when we get the most extreme tides. Kind of sucks for us because that's when we generally have the strongest storms, nor'easters and things. And if we have a nor'easter which happens to come ashore during a king tide, that's when Boston gets flooded. So yeah, most extreme tides and most extreme storms, and that's just kind of how it is. What do we learn? We learned what causes the tides. It's this stretching thing about the difference in gravitational force between one side of the Earth and the other compared to the moon. We learned that the sun does influence tides as well, but not as much as the moon, and that depending on the phase of the moon, the sun's tides and the moon's tides can combine to become more extreme or can tend to cancel each other out a little bit, and that's spring tides and neap tides. And finally, we learned that the seasons also influence the tides. In our winter time, the tides are most extreme because that's when the Earth is closest to the sun, and when the moon also aligns up closest to the Earth during that time, then we get our most massive tides. Okay, thanks for your time. We will see you next time.